There we go. Okay. So I'm going to put givens in. They're going to be K, M, and some initial conditions, okay? I forgot our time matrix. Let's calculate natural frequency, the amplitude, phi, and then x. Okay, all this is in your notes that you had last time. Okay. RT of K over M is SQRT of omega n squared times x naught squared plus V naught squared divided by omega n. And then phi is A tan of omega n times x naught divided by V naught. Yep. That's the omega n is the natural frequency. And then finally x. Just going to save it as downloads. Call it Untitled 2, but you call it whatever you want. Bless you. All right, let me put this. Okay, I didn't get any issues. If I type X, there we go. So X should be 1 by 801. Oh, let me zoom in, sorry. I'll copy this and we'll talk about it, okay? if you remember from last class, the top subplot is going to be a square that's going to go oscillate up and down. And then the bottom subplot is going to be a square that vibrates back and forth, simulating what X is going to do for you, okay? And you'll see where I use Y here in a minute, okay? Now, for the animation, we're going to use a loop. So for I equal 1 to length of X, subplot 2, 1, 1, set data time of I, Y data. I guess it doesn't matter. X of I, marker, where's color B. Axis. Max and min time. And I'll pause here after I get this done. Let you catch up. Oops. So max time min X. X. And then we're going to plot min of time, max of time, You're getting there. I think you're getting to be dangerous now with MATLAB, right? No? All right, let's do subplot 2. Okay? So we're going to set H, which is the plot on subplot 2. X data. It's going to be X. Y data. It's going to be Y of I that we had above. Marker. Let's do square. Marker size 60. Color blue. Next. Really, I would copy and paste these 3 lines. Whoops. Down here and change them. So axis is min of X minus 0.25, max of X plus 10, 10. And down here, 0, 0, negative 10, 10. Y tick. I don't think so. Let me see here. Let me run mine and see. Did I miss something? So max, min, max, Yeah. No, don't look at it. The bottom graph looks okay, sort of. Oh, you know what I forgot to do? Oh, can someone tell me what I forgot to do? I forgot one line. Look carefully. What? Yeah, I forgot to put subplot 2, 1, 2. Who got it?
I was curious why you put that there,
How about this? I'll bring in something next class. That could be a good test question right there, right? Now try it. One line. Mess everything up, right? Yeah, look at your computer. Yours is slow? Yeah. Because the process is yeah, look how fast yours is going. This is the school computer right there. Oh my, why is yours so fast? Okay, now, homework 4 is dealing with this differential equation right now. Okay? This has a viscous damping effect. Okay? So, like a shock with oil in it. Okay? Or a shock with no oil in it. It's going to have different characteristics. Okay? Zeta is what defines the characteristic. It could be less than 1, it could be greater than 1, or it could be equal to 1. Okay? There are 3 solutions to this that satisfy that. Okay? I'm going to give you the solutions for each one. For zeta less than 1, I'll write the equations. Okay? What I want you to do is create a code where you have these givens, K, M, and initial conditions, and a zeta. You have to tell me a zeta. Okay? Or you're going to send me the code. I'm going to pick zeta less than 1, equal to 1, and greater than 1, or 0, and I want it to spit out the answer. Okay? It'll be a graph, yes. And on top of that, I want you to make a switch case to say yes or no for an animation. Okay? So this code is probably going to be pretty lengthy. It's going to have if-else statements and a switch case scenario. Okay? So the switch and case are going to be for yes and no for animations. Okay? You could actually probably do that right at the end. All right? Once you get all the values. But it's going to have if statements for zeta. So if zeta is less than 1, do these calculations. Okay? Does that make sense? What I want you to do for this homework? So if zeta is 0, what's the solution? We just did it today in class. Doesn't have any damping. So you already wrote that part of the code. You can just copy and paste it, right? You already did the animation too, so you can copy. But putting the switch in case, how to do that? That might be, that's the learn. Like I want to refresh that. Yes. Yeah, I'll show you those. Yep. That's what. Yeah, it's if it's underdamped, it's less than 1. That means it oscillates and then finally levels out. If it's critically damped, equal to 1, that means it'll start either up or down and go right to level. It'll stop. Okay. Overdamp means it'll start maybe at like an X value of like 1, and it'll go and it'll actually move. Like say you have it here, it'll move past equilibrium and come back and stop. Okay. And then when it's 0, it's just going to keep oscillating. Okay. So you'll have 4 cases. So anytime you change zeta, you'll be able to see exactly what happened. Okay. So let me just write these equations down for you. And I forgot my notebook, so I'm going to go get that. Okay. Because I can't remember these equations off my head. All right. All right. Underdamped. Zeta less than 1. Thank you, Andrew. I'll try to be as neat as I can because these are kind of long equations at times.
Give us the end code if you want.
The N code.
Yeah, like the answer.
You like how he operates?
It's worked before.
So you should be able to write the code and have all your givens in the front. And you just change those and it automatically spit out what the correct answer would be, okay? So this is still underdamped.
I pulled the no. Eqns, how do you get the negative?
What is that?
That's arctan negative.
Nope, that's a tan, that's inverse tan. So you'll never get a zeta that's negative. It'll be less, it'll be from 0 to 1, or actually 0 to 0.999, 1, and then 1.00001 to whatever, okay?
Yeah, but Eqns is. Oh, yeah.
Yes, oh yes, a tan is the, yes, yep, yep. Now, do you see how I have x parenthesis t?
Yeah.
That's saying that x is a function of time. So you can't really do that in MATLAB, right? You can't have it on the left of the equal sign. So just write x, right? Okay. And it's AE, and it's negative zeta omega nt. That's what the E is raised to, okay? Then sine omega d plus phi, that's all times E and A, okay? I hope that makes sense. Omega d is just omega n times square root of 1 minus zeta squared, and then you got A and phi. So how would you check to make sure that this solution works? You plug in, right? Okay, you plug into what that differential equation that's on your homework, okay?
Did you post that?
Yes, it's in homework 4, yep. And the graph should look like that on the right, some form of another, okay? Can I move up? Is that okay? We'll do overdamped. Zeta is greater than 1. This one is the, not too bad, but x equals e to the minus zeta.
You have to do something
What does it say?
Oh.
Thank you. Did you do any of this in differential equations? No. Because for me, like,
If he did, no one was paying attention. No one was,
I mean, you're paying attention, but.
it's not the math, more like his movements.
because to me, this is like the fundamentals of differential equation is these 3 cases right here. Because this is,
We didn't really get anything in depth.
no,
It's very on the surface.
okay.
And we just, I don't know, we like taught us how to do certain types of differential equations,
Yep,
but the application was never there. Right. So I didn't remember any of that.
okay.
And I was good at doing whatever we wanted, but.
Didn't quite understand where it was used then. Well,
That it existed and that was, like, you use it for engineering and stuff. We did differential equations to do differential equations.
okay. Well, hopefully, I know this is advanced programming, but Hopefully you're getting a little bit more understanding of things. Especially next time. I might actually fix homework 5, so you pick your own differential equation and solve it. Maybe you find one in circuits or wherever. Okay, there are tons. This should go like that. It actually is over damped, meaning it's a little bit too much. So typically it goes over like once, that's it, and then levels, and then goes back to equilibrium, okay? And then can I do the last one here? Do it in green, critically damped.
Critically, like on top or bottom side. Maybe it's positive.
Yeah, it doesn't matter. It could, so when it's either positive or negative X, meaning if I have a spring mass system here and I move it this way, that's positive. If I move it that way, it's just negative.
All right.
Yep.
This number is like data, is it between -1 and 1?
Nope, zeta is always between 0 and greater than 1. If that made any sense. It's 0 to whatever. It's never negative. Zeta is never negative. Okay. Nope, not zeta. X can be negative because your equilibrium defines positive and negative. Okay. This one's the easiest one.